Yeah,
Okay,
well,
so
it was a really good explanation for those of you who were here. So,
Can you explain again why eccentric has more force? I was trying to write it down.
you were trying to write it down. Okay.
Yeah.
So again, as the lengthening, and we talked about, for those didn't hear because it wasn't recorded, sorry. When you're lengthening, if you're pushing down, you're trying to pull up, and you're and the bar is pulling down and you're losing. It really is, eccentric contraction is you trying to pull as hard as you can one way, and in fact it's being pulled out for you. And yes, you can create more force in the muscle when it's doing that, going that way, and there are several reasons for them. Number one, there are, if you think of your cross bridge is trying to form and then pull. That's what it tries to do. It forms and pulls and creates that tension. That's your concentric contraction. That's what it tries to do. If it's losing, it means that it forms and then it gets pulled out the other way. And as I talked about, the hands on the rope in a tug of war, the concentric is you pull this way, the eccentric is you've got hold of it and it's being pulled out away from you. Even though you're trying to pull it in, you're losing and it's being pulled out away from you. That act of pulling out away from you stretches these elastic components that are inside the muscle, called series elastic components, and that adds to the force output of the muscle beyond just what the cross bridge can do on its own. And so that's going to increase the amount of force. And there is also, in an eccentric contraction, there's some variations in how long the cross bridge can stay formed, and how easy it is to recycle and grab a new binding site. That answer it?
Yeah, thank you.
Any other questions on the force length?
yeah, I just want to clarify, because both cases of the force length and the force velocity, it seems to be that cross bridges are the reason.
There's what?
Cross bridges, right?
Well, yeah, because cross bridges are what create force in the muscle. That is what actively creates force in the muscle, is the cross bridges. And the more cross bridges you have formed at a certain period of time, the more force you're going to have. Within the force, again, your force velocity curve is always, this is for an instant, a certain amount of activation, in this case 100%, which is what it's usually shown as, and always taken at the same measurement. There was just somebody who had their hand up. Do you still have your hand up? Or, yeah, Brianna?
I did, sorry, but is this, what question is this? I don't want to repeat it.
This isn't a question. The question was explain the force velocity curve.
Oh, okay, then I'll ask you my question later. Sorry about that.
No problem. Okay. Yeah, so this is the force velocity curve, and we're just talking about what it is and why it happens. And it comes right down to, again, these cross bridges forming and just having to release, recycle, grab, release, recycle, regrab, and you lose some force, as I said, due to the velocity of moving through the center of the material in the cell. So that's one of the reasons why you lose it in the concentric, plus just the active of the time and the fewer you can have active as you're moving that quickly. So, any other questions on this?
So just to confirm, when you increase the velocity in the concentric, you're losing the force, right?
Yes, you cannot generate as much force when you. So again, we'll go back to our machine. And if you've put your, again, it will come up at a constant velocity, which would mean that, or you can at least try and make it so that it's somewhat a constant velocity for the muscle. And as it's coming up and you're pushing up as hard as you can against the bar that's going at a constant velocity, as you speed it up, you cannot push as hard on that bar as you did when it was slow. You can't. And there's a certain point where at a certain velocity, you can't really generate any more force. And that is the concentric end of the force velocity curve. Okay. Any other questions on the force velocity curve?
There was a question in the textbook that was asking how strength training affects the force velocity curve. I'm just wondering, like, is that the same diagram that you just drew out? Or do they mean like as your strength increases over time, what happens to the force velocity?
Well, so it's as your strength increases over time, what does that do to your force velocity curve? I mean, it certainly will increase it here. Sorry, whoops, that doesn't happen. Here, right? Depending on what the training is, and this is a bit, if you're just increasing something by a percentage, the reality is if you increase a percentage of 0, it's still 0, right? So if it's just a pure increase of force by a percentage, it's going to do that. I mean, there's really two ways that it can do it. One is by percentage, and one which is absolute. Absolute would look something more like this. So if it's an absolute increase in you would also increase the force, the velocity that you can do it at. That's not as realistic as increasing by a percentage, where the velocity doesn't change much, but the force that you output that you get along the way does. Either way, you increase power, because power is velocity times force. So you actually get more power in each of these situations. So.
Thank you.
You're welcome. Okay, anything else on force velocity? Okay, I will stop sharing. And yes, now, Oriana, what did you want to ask?
Okay, so this is on chapter 6.
Yeah.
The additional problems.
Mm-hmm.
Number 2, can you go over that one?
Yeah, okay. I can go over that one. Let me just share a whiteboard again. Okay, so going down, we have a consideration of the force length relationship and the rotary component of the muscle force. Sketch what you would hypothesize to be the shape of a force versus joint angle curve for the elbow flexors. So we have let's just force length. Theoretically, now force length curve, when we talk about it, force length curve is really the length of the muscle, which is proportional to the angle that you're at, but it's not necessarily the same as. But we'll go with that for now. So you have your force length curve, and this is the force that output of the muscle. And let's just review what the force length curve looks like. We have two portions of it. We have the active, which is the black. We have the passive, which is the green, and then the blue is going to be the two added together. So, I mean, I'm literally going to add, that much onto here. Oops. And that much onto there. So it's going to come down, and then it's going to take off like that. So the blue is the actual force length curve. The black portion is the active part. That has to do with the actual number of cross bridges that can be formed just because of the length. It essentially is the optimum pairing of the actin and myosin, so the most binding sites are available. And if it's too short, they can't go, there's not as many binding sites available because they're beyond it. And if it's too long, it's like, again, I've talked about a tug of war. If the rope starts to no longer be at the anchor and slide through people's hands, so not as many people can reach it anymore, that's going to be this long end. How does that reflect in your joint angle? Well, for an elbow, this end is going to be the end where you have, if that's your elbow joint, where your elbow's really brought up, basically your hand is brought up to your shoulder. And this end is going to be the end where you're stretched out. And to be honest, the resting length for the elbow is roughly, it's near 90. I think it's a little closer to 100 degrees, but ballpark 90. So theoretically, that's what it should look like as you're going out. Okay, as when it's really long, there is force in that muscle. It might not be very useful force, but there is force in the muscle. And then you get more and more as you come to the middle, and then it gets less again down here. It's harder to shorten the muscle there. At the same time, we have the fact that, let me just try and draw this in a more. So at this end, if I looked at my forearm, my biceps would be pulling this way, right? And at this end, my biceps would be pulling this way, right? So this one has a dislocating component. This one has a well, one's dislocating and one's stabilizing component here. Now, in here, the actual force that's actually causing rotation looks like that, right? And in here, the component that actually causes rotation looks like that. So it's somewhere in between here. Where the muscle is actually doing that, right? And at that point, you can, almost all of the muscle is rotary, so it's going to cause strength. It's the rotary component that causes the strength. So this part right here is the actual force in the muscle. This part right here talks about how much of it actually adds to strength. So one is the force in the muscle, one is adds to strength. So in this over here, the muscle force is small and the component is small. Here, the muscle force is larger because we're stretching it, and a component is small. And here it's maximum. So it's going to not only give a large amount, sort of the best amount of active force that you can get, might not be the most force that you can get in the muscle, but it might be the most active force you can get. And at the same time, that force that you're getting is all going to be to rotary, which means it's all acting to actually rotate your forearm around. So it's actually going to be strength. So again, this is the force in the muscle, but it's not necessarily what actually we measure as strength, because what we measure as strength not only includes the force of the muscle, it also looks at what that momentum, how much of that force is actually rotating the joint segment around. So the rotary component of that force. So it just happens that in the elbow, the resting length, meaning that active maximum active component is pretty darn close to the point where we also get the largest rotary component. That help? Any questions on that? If you do, unmute and okay. Clear that then, and
Dr. Moore, sorry, I just had a quick question about that one. So that was the force length. Would it still be the same then for the force and the elbow angle?
well, that was the elbow angle, the force length and the force and the joint. That's what I was trying to say, is that the elbow angle and the length are related. Like when I draw the reality is what they're trying to get you to is the fact that that's torque and joint angle. And the torque is this force length times the rotary component times joint angle. And length is proportional to joint angle. It's not perfect, but it's not one-on-one because there's an angular piece to this. But the reality is that as you go through a range of motion of a joint, the muscle length goes all in one direction. So as I go from this posture to this posture, I am literally going through that direction on my force length curve.
Okay, makes sense. Thank you.
Yeah, because that's one of the main premises of this, is that you change the length of your muscle because of the posture you're in. Any other questions on that one? Okay. So again, you have to always unmute and ask when I'm in, because I can't see chat when I'm in share. Okay. So when the top of the graph, left on the graph was short, right on the graph was long. Okay, Brenda.
Can we do question 5 and 6 in chapter 6, additional problems?
Yep.
I kind of don't get why in they use sine and cos. Like how do you get to choose what if you to use sine or cos?
Yep. Okay. Let me just share that one again. No, not that way. Sharing whiteboard. Okay. So 5 is, first of all, we can either have the parallel fibers or we can have the pinnated fibers. Why do we want the pinnated fibers? Because when it comes right down to it, the physiological cross-sectional area, so if I have a tendon, and then I have a muscle with a whole bunch of parallel fibers coming down to another tendon. So the actual force in the tendon is going to be, all of these, the force in all the fibers is going to add up to be the force that's actually in this tendon. And in this tendon, right? And if you try to figure out what that force was, it's related to the physiological cross-sectional area here, which is, the area from here to here. If I cut the muscle there so that you can see that cross-sectional area, that is proportional to how much force you're going to get out of the muscle. It's called physiological. It's the anatomical cross-sectional area because it's 90 degrees to this line of pull of the tendons, but it's also the physiological cross-sectional area because it's 90 degrees to the fibers. Physiological cross-sectional area, which is the part that's proportional to how much force you can get out of a muscle, is, again, always cut perpendicular to the fibers, not the tendon or line of pull of the muscle, but the fibers. So that's what we get with a parallel construction. If instead we were looking at a pinnated, we have tendon 1 and tendon 2, and we'll just go with a unipinnate for now. And then we have a whole bunch of fibers that are pulling, and they're pulling at an angle of pennation. And the angle of pennation is the angle of those fibers, of the fibers to the tendon. That actually allows us, again, it's the physiological cross-sectional area. And what would the physiological cross-sectional area be here? Well, I would have to be trying to find a line that would be 90 degrees to those fibers. So it would literally be, that's not quite 90 degrees to them. Don't think I can undo that one, sorry. But if I was to find a line that would be better. That's better. 90 degrees to it, okay? And I'm trying to find the area from there to there. I can actually put more fibers in parallel in the pinnated, which become the physiological cross-sectional area in the pinnated structure than I could in the parallel, because in the parallel, the muscle just has to keep getting bigger and bigger and bigger in order to do that. Whereas in this case, it's not getting wider. Yes, it's getting longer this way, but it's not getting wider this way. So that's the advantage of the pinnated muscle, is that we can get more muscle fibers in parallel, and therefore they can create more force. There are some other pros and cons to this in terms of length and velocity responses, but just overall you could get more. But there is a cost, and that cost is that those fibers are not pulling directly along the tendon anymore. The fibers are going to pull in that direction. Let me just reiterate that. That's the direction the fibers are going to pull. They're going to pull that way and on that fiber and that, or on that tendon, and that way on the other tendon. So we have a muscle force that's pulling on the tendon like this, and that literally has a component that's along the tendon, and that's that's along the line of pull of the muscle, and a component that just is kind of going to bring the two tendons together. So one part kind of brings the two tendons together. One part actually is along the line of the tendon, and that's what's actually going to pull on the bone, which is what you want the tendon to do, right? You want the tendon to pull on the bone so that you can rotate the body segment and you have movement. So this component right here, which is the portion of the tendon of the fiber force that is along the tendon. So this is the fiber force right here. And this would be the portion of the fiber force that is along the tendon. And this, so we're literally taking components of force, just like we've done with components of all vectors along the way. You have you're going to have your force of your fibers. You're going to have the force of the fibers along the tendon. And you're going to have an angle here, theta. This is the portion we rarely ever calculate, but it is there. And this guy right here is always the, the angle of pennation is the angle between the tendon and the fibers. So you can see the force of the fibers along the tendon, which is what they want us to calculate, is adjacent. So force of the fibers along the tendon are always going to equal the force of the fibers. Oops, sorry. Just get rid of that for a second. Are always going to, because this one's, yeah, that's, sorry. It's going to equal the force of the fibers times cos theta. Why cos theta? Because it's adjacent. It is adjacent. So in the first one, in question 5, it says you have a pennated angle oriented at 45 degrees. So that means that theta equals 45 degrees. And we know that the force of the fibers equals 150 newtons. So this portion, which is the force of the in the tendon, is going to be 150 times cos theta, cos 45. Which is going to be 106 newtons. Okay. Now, in the second question, number 6, it says that it's a pennated muscle aligned at 60 degrees. So this is question 6. Let me just erase these guys again. And change colors because I just want to. So we have a theta, angle of pennation equals 60 degrees. And we have the force in the tendon this time, which we're given, equals 200 newtons. And therefore, if we come back to that same thing, the force in the tendon equals the force in the fibers times cos theta. Now we're trying to figure out how much force had to be in the fibers. force of the fibers. Okay, that's going to be force of the fibers. Newtons divided by cos 60. I think cos 60 is 0.5, so that's going to be 400 newtons. That makes sense? So it's always
Yeah.
cos. Always
Yeah,
cos.
yeah. I was trying to reason why they always use cos and then sine, and I just didn't want to cram it, so that's why.
Yeah.
I had one question.
Yep.
Yeah, it was more so about the diagram you were drawing on the pinnated muscle fiber.
Mm-hmm.
Was it that you can generate more force with parallel or pinnate?
You can generate more force. That's actually a complex question, and I'm really simplifying it at this level for you guys. But you can have more force generating capacity. You can have more force generating capacity in the in a pennated muscle because you can have more parallel fibers. Now there are other things that happen, like there's just more fibers in parallel that you can get into a pennated muscle. So you can get a greater cross-sectional area, physiological cross-sectional area, not anatomical cross-sectional area, physiological cross-sectional area. So yes, you can do that with that. But again, you take a bit of a hit on this. And the other thing you don't get is as good a you don't have the same force generating capacity over a range of lengths and a range of velocities. So it's kind of good to have a couple of different architectures of muscles crossing a joint, because especially one that goes where you want to have force strength over a range of postures and velocities, because these ones have shorter fibers, and if you have shorter fibers, you don't have the same range of force length capability. It's a little bit more limited. So that's why I say it's not a as good it's not as simple as saying yes, you get more force out of a pennated. You tend to be able to have in a pennated muscle a greater physiological cross-sectional area, so therefore a greater capability in general of possibly creating more force, but it's very muscle specific. It's just that but it also has some other limitations. I'll leave it at that. Does that answer that?
Somewhat, but yeah, I get an idea, because as though like you said, physiologically the cross-sectional area in the pinnate form more. So,
You can, like, I mean, basically, you think about it, you have a bunch of fibers. Hold on just a second. Okay, sorry. you have a bunch of fibers that are that you can work with. I mean, ultimately, and those fibers, sorry, you not just fibers, you have a bunch of sarcomeres, right? Think about these sarcomeres, which are the building block of the muscle fibers. And the more you add, the more mass you have. And we can't be that, can't have huge masses of muscle, because there's a fine line between being able to generate force and needing to have the force be so wide that it's that the mass of the muscle be so great that it takes too much energy for us to even drag that muscle mass with us. And even more importantly, for that muscle mass to be in the way, so that we can't, if we have such great muscle mass, we can't even go through the range of motion. So there's limits, right? So we have all these sarcomeres, and they can be built into different structures. And we could have a couple of muscles, fibers, that were, let's see, 1, 2, 3, 4, 3. So this muscle right here and this muscle right here have the same muscle mass. Clearly, the one on the left has a greater cross-sectional area, so it can create more under optimum conditions, under the optimum length, and let's just go with an isometric. The one on the left can create more force than the one on the right, because the one on the right doesn't have as large a cross-sectional area. But the one on the right, each one of these sarcomeres has sort of the same range of motion that it's good for. So you should be able to add up all of the ranges of motion on this one on the right, and you're going to have a greater range of motion that it can generate force in, because there's more sarcomeres in line with each other than there is on this one. So that's why I was saying there's pros and cons. You can, in the pennated muscle, you can usually build up more fibers in parallel, therefore a greater cross-section. It has the potential for a greater cross-sectional area. Physiological, but this guy, you have a greater range of motion from which you can create force. That help?
Yeah, it was clear. Thank you.
You're welcome. Somebody asked me about question 7, whether the answer was, the first answer was wrong. It was not wrong. I apologize. I made a mistake when we first came on, and I wasn't thinking clearly. I didn't read the question, which I really should have. The answer of 1.7 centimeters squared is correct, because it's not the 106 that is the physiological cross-sectional area. It is the force being created by the fibers. It's the 150 that is the force being created by the fibers. If anybody was on when I was listening to that. So 1.7 is correct. Any other questions on this?
Yeah, I also have a question.
Okay.
Can you hear me? So when tendons are starting pulling together, so the angle is changing, right?
Well, that's a very good, very advanced question, and you're right. You're absolutely right now, and that does change the. So as you go through the range of motion, and or with different types of contractions. Yes, you're right. The angle of pennation can change. There is some absolutely fascinating research out there on this. And they have actually put onto, so for example, they put it onto a ultrasound onto the soleus muscle while somebody's walking. So on the calf muscle there. And what's really interesting is that our body has different ways of dealing with this. In some of the cases, as it goes through that range of motion, what happens is that it uses that change in angle to actually change the length of these fibers. And it actually, remember I said here that you have a greater range of motion. By changing the angle of this as you go through, it actually allows the muscle fibers to stay at a relatively constant length so that the fibers are actually, now again, this is not something that I would ever test you on but I want you to realize that there's a lot greater depth in this than just that, because think about it, it actually is rotating a bit in order to keep the length of the fiber the same. So the fiber is almost contracting, well, nearly isometrically, even though the muscle is shortening or lengthening. So it allows for, not having the fiber change length, even though the muscle is changing length. So there is some very interesting research on that topic that, because you're right but you still are going to lose a portion of your force to the fact that it's at an angle and not purely in line with the tendon.
Yeah, but it becomes bigger for the portion of force which aligns with tendon. So when angle decreases, so the portion of force.
If the angle changes, you are absolutely right. You're going to change the amount of force that goes along the tendon. So, it becomes it's like the idea that the force length, like the question 2 of additional problems where you really strength is both that combination of the instantaneous length of the muscle and therefore the force output of the muscle at the same time, how effective that muscle is actually at creating a torque at that angle, at that particular. So you've got more than one thing happening at the same time. You are right, as you go through the range of motion, that angle could change, and therefore the angle could, how much force is actually going down the tendon is, will change.
Mm-hmm. Yeah, it's more complicated than
Exactly.
Thank you.
Any other questions on this one?
I just wanted to be sure. So, like, when do we use sine then? Like, how do we need to use sine instead of cosine?
Did you see me use sine at all?
No, I didn't.
In this particular case, if I, asked you how much force, which I'm sorry, I've never asked and I can't imagine asking, but if I asked you how much force did you, that's not even how much force you lost. At this level, we're really not going to talk about the component of the force that is perpendicular to the tendon. Really, what is important for you to understand at this level is that the fibers create force, and that because the fibers are pulling at an angle to the tendon, it is the component of force that is along the tendon that is what we see at the tendon bone interface, right? And so that is the important part. And so as long as the angle of pennation is between the tendon and the fibers, it's always going to be adjacent, which means close.
Okay, thanks. I was just asking because I've seen in the textbook that they use sine for an example there, so I just was confused.
So where does that, which page? Which page in the textbook did they use sine? For that,
Before, sorry, I don't know if you heard that, but
I didn't hear that, sorry.
it's page like 164, 165.
164, 165.
But they are asking for the force perpendicular to the muscle there, which you said you're not going to ask us about.
So, oh, like in one of the questions?
It's not an assigned question. It was like an example in the textbook of them answering a question.
Of them answering a question. Okay. Again, 154 maybe? If you could tell me which question, I could talk to it.
It says sample problem 6.2.
Okay, now that is completely different. That is not an pennated muscle question. That is a rotary component and a stabilizing slash dislocating component question. That is very different. And yes, you do need to use sine for that. That is the case. We're not talking, the ones that we were just talking about where we used only cos was looking at the effect of fibers pulling on a tendon, not the tendon pulling on the bone, but the fibers pulling on the tendon and how much of the fiber force is actually going along the tendon. The questions like question 6.2, which absolutely you need to use the sine for, are questions where you have a, so I wanted to make sure that this wasn't happening. So you have a, let's go with the normal forearm, and we have an elbow and we have a biceps, and that biceps, the line of action of the muscle is always from the, from the origin to the insertion here, and it is always pulling on the bone. And so that's my line of action of my muscle. And this is the angle of insertion. It is not the angle of pennation. It is the angle of insertion of the muscle. So it's a different angle. So that theta right there is the angle of insertion. So it's what its insertion, what angle it's inserting at. And this would be the distance of insertion. Or distance of attachment, either way. This muscle could be going in at different angles. So if we went here, and let's say I have my forearm, is straight up here, my muscle would be more like that here. Or if I, have my arm bent, so that realistically, if you looked at my upper arm, it would look like it was here, then my muscle would be pulling in this direction. And in each case, this angle right here is the angle of attachment, not the angle of pennation, but the angle of attachment. And in all of those cases, I get two components. I get a rotary component, which is 90 degrees to the muscle, and I get a either stabilizing or dislocating component. So this would be stabilizing. Let's do something a different color. Stabilizing, stabilizing, dislocating. And in those cases, in all of those cases, if that's F, 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 and that's F rotary, and this is F stabilizing. F rotary is always, because that would be the equivalent, that would be the same as doing that, right? So it would be opposite, is going to be force times sine theta. But in this case, that theta is the angle of attachment of the tendon attaching to the bone, not the angle of pennation, which is the angle of the fibers attaching to the tendon. So different angles. And yes, sine is very important there. And the stabilizing component is going to be F times cos theta. Fair enough? That so answer the question?
Yes, thank you.
You're welcome. I'm glad you told me which number it was so I could clearly say, yes, sine is important. It's just a different angle, different situation. Any other questions on that? Okay. Any other questions? On anything? Does that clear up all of muscle?
Would we be able to go over question 8 from additional problems for chapter 6?
I'm sure we could. What's 8? Oh, that's a good one. Yes, absolutely. That's an important one. Let's share that one. So question 8, page 164, chapter 6, additional problems. If the biceps brachii attaches to the radius 2.5 centimeters from the elbow joint, produces 250 newtons of tension perpendicular to the bone, and the triceps brachii attaches 3 centimeters away from the elbow joint and exerts 200 newtons of tension perpendicular to the bone, how much net torque is present at the joint? And will there be flexion, extension, or no movement at the joint? So, we have our forearm hand. We're going to have an elbow joint, and in this case, I'm not going to put the elbow joint at the end because it's just easier to draw your triceps this way. I have a force of a biceps over here, and I have a force of a triceps here. So think of this as a, if it's held in place right here, that's held in place, and you pulled up on this side with the biceps, hopefully you can see that it would try and rotate it that way. So that would be the torque of the biceps. We never show those on the same free body diagram, but I want you to see what's happening on here. Whereas if it was the triceps, it's trying to rotate again. If this was held in place and you pulled up on this side, you would expect a torque of a triceps to be that way. Okay, so again, not a proper free body diagram, but I want you to imagine what would be happening here. If you can practice with your own pen. So you have your pen, you're holding it where the joint is. The biceps is on this side of the joint. It's going to pull up. It's going to rotate my pen that way. My triceps is on the other side of the joint. It's going to rotate my pen the other way, which makes sense because biceps brings it this way and triceps the other way. So that should hopefully make sense. Okay, and it turns out the net torque that you get is just the two added together. One's going to be positive, one's going to be negative. So I'm going to just create a reference frame so that you can see which one this is what I consider positive theta. You're going to be doing free body diagrams, and you'll note in the free body diagrams, which is the next lecture after muscle, I always put that reference frame in there just for this type of situation. So we have the force of the biceps is going to equal 250 newtons. And that distance of attachment is going to be 2.5 centimeters. And for the triceps, the force of the triceps is going to equal 200 newtons. And the it's going to be 3 centimeters away. And that is 3 centimeters. In both cases, we're told that the muscle is pulling 90 degrees to the bone, so we don't have to worry about that angle of insertion and the rotary component or the stabilizing component, because it's all rotary component when it's acting 90 degrees to the bone. Okay, so the torque created by the biceps is going to be 250 newtons times 0.025 meters. Which is 6.2. Oh, good. Somebody was going to tell me. 6.25
Yeah, that's right.
Newton meters. And the torque created by the triceps is going to be 200 newtons times 0.03 meters, or 6 Newton meters. That one I can do. So the sum of the torques around the elbow is going to be
6.
the biceps minus the triceps. Why minus? Because I'm considering this would be counter, as I've drawn it, this would be counterclockwise, so I'm causing it positive. So 6.25 Newton meters minus 6 Newton meters, which equals 0.25 Newton meters. And which direction is it moving?
It's flexion.
Exactly. It's flexion because the torque being created by the biceps is greater than the torque being created by the triceps. It's not the force. Yes, the force is greater in the biceps than it is in the triceps in this particular case. But it's not, that is not the reason why this is, it would be the torque is bigger in the biceps, so it wins.
I had a question.
Yeah.
I just want to clear something up that you mentioned. I'm not sure if I caught it correctly. Was you said you don't need to worry about the rotary component because it's the force is acting 90 degrees onto the forearm?
Well, what I mean to say by that is that it is completely rotary component, that when the muscle acts 90 degrees to the bone, then it is 100% rotary component. So I don't have to take that extra step to figure out the rotary component and the rotary component and the stabilizing component. I don't have to do that in this case because I know. It's not that I am saying you don't worry about the rotary component. It's that I'm saying is that you know when it's acting 100%, 90 degrees to the bone, it is 100% rotary component. Does that help?
Okay. That makes sense. Yes, I'm thinking about it. It makes sense.
Oh, good, good. I'm not dismissing rotary component. I'm just saying we know that it's 100% rotary component in this case. Any other questions on this one? I mean, this is one of those ones where you can do a lot of what ifs here. So if the biceps keep doing the same amount of force, at what point will how much force do you need to have in the triceps for there to be no movement at all? So that would be a case where you want the sum of the torque around the elbow to equal 0, because that would be where the flexor torque and the extensor torque are equal, which means that the biceps minus the triceps equals 0. And so that would be a torque in the triceps of 6.25 Newton meters for it to be the same. That would cancel out what's happening in the biceps. And for that to happen, the force in the triceps is going to equal the torque in the triceps divided by the moment arm, which is 0.03, which would be 6.25 Newton meters divided by 0.03 meters. Meters will cancel. I'll be left with newtons. How much force is that?
$208.3.
Okay, so that equals 208.3 newtons. Now, I know there's no answer to that, but in the book, but it's one of those, well, what if questions. You know, how much force do you have to have in the triceps in order to balance out what's happening in biceps? And you can see quite clearly here the fact that, you know, at 208.3 newtons, it still has less force than is in the biceps, right? And yet it balances out, and it because of the different moment arms. The biceps has a smaller moment arm than the triceps in this particular case. Any questions? Okay. Oriana?
Okay, so this might be like really simple to answer, but I had a question about chapter 6 for the additional problems number 1. So the second half of the question I'm a little confused about. So it's like the source of the forces causing motion at each joint. So I'm a little confused about that.
So question 1 in additional problems. Identify the direction of motion, flexion, extension, etc. at the hip, knee, ankle, and the source of the forces causing motion at each joint for each of the following activities. So if you are sitting down in the chair, you've got two things. You've got a direction of the force and a direction of the joint. And so it's basically a direction of the torque. and a direction of the joint. And those are not necessarily the same thing. And this is a really, really important concept, is that the force of the muscle is the torque that's being created. The muscle group that is active is the muscle group that needs to be on for you to do what you're doing properly. And if the direction of the muscle joint tells you what the actual motion is. You put the two together and it tells you whether the muscle is contracting eccentrically or concentrically, which is really an important concept. So if I'm sitting down in a chair, so I stand up and I sit down. If I sit down slowly, where I'm going to feel it in my knees, let's just think about the knees for now. As I slowly sit down, feel your knees. Do you feel it on your quads or do you feel it on your hamstrings? Anybody? Just as you sit down slowly.
You feel in the quads?
You're going to feel it in your quads, which are your knee extensors, correct? That's why we take anatomy here. So they're the knee extensors. So they are actually the muscle. And in a few lectures, you'll understand why this is the case. But so as you're sitting down slowly, you're going to feel it in the quads, because it is the quads it's your knee extensors that control your sitting posture. But your knees are flexing. As you are going down into that seated posture, your knees are flexing, which means that you actually have eccentric contractions of your quads. That's a really important concept. It's the eccentric contraction of the quads. Yeah, and so that's what this is sort of that first step in it, recognizing that as you go through a range of motion, you're going to change the angle of a joint. And at that same time, you're going to use primarily one side of the joint. One side of the joint is going to be the agonist. The side of the joint that's going to be the agonist is the muscle that you have to have on. You have to have on to do the activity that you're doing the way you're doing it. If the muscle on the other side of the joint, in this case, the hamstring, was on, you would sit down really quickly. If you actively flex your knees as you sat down, you would go whoosh down into the chair. And that's not how we usually like to sit. We usually go down in a slow, controlled way. So we turn on the quads and they eccentrically contract. They are the agonist. The book sometimes says that agonist is the concentric contraction of the muscle. And later on, it disagrees with that later on. It's too simplistic in this chapter. The reality is the agonist muscle is the muscle that you need to have on to do the activity. And if your activity requires that muscle to lengthen, meaning you've got your extensors on, but you're flexing, that's always going to be a situation where the muscle is lengthening, which means it's an eccentric contraction. And this problem is one of those ones where they're trying to get you to think through which muscle group is active during different portions of it. And as you go down, kicking the ball, let's think of kicking the ball. So kicking the ball, you're going to bring your leg back and then kick it forward, right? It's going to come back and then it's going to kick forward. As you bring it back, let's just think hip at this point in time. So you bring it back, you're going to have your extensors, your hip extensors on, your glutes, right? to bring it back. And then as you stop, as you try and slow it down, so it doesn't just come to an end, we're going to slow it down by turning on the muscles on the flexor side to slow it down. And then immediately we're going to keep those flexors on to bring our leg through. If we wanted to do it with just the knee, if we were kicking with just the knee, we'd be turning on the hamstrings to flex our knee. And then we would turn on our quads to stop the knee from flexing. And then we would keep the quads on to extend our knee to kick the ball, depending on whether you were kicking from the hip or kicking from the knee. That's the scenario that would happen. What's really neat in that scenario is that, again, you're going to turn different muscle groups on throughout the activity, but in that particular situation where you turn the quads on to slow your knee from going back, and then immediately do a concentric contraction of your quads. So it's an eccentric followed by a concentric. That's called a stretch shortening cycle, where during that eccentric portion, if you were on earlier when I was talking about force velocity and the effect in eccentric, one of the things that happens with eccentric is that we stretch these the cross bridges and anything in line with the cross bridge. Some things, what we call series elastic components, which are just basically stretching of any proteins that are in line with the cross bridge. That the cross bridge has to be on and formed for this to stretch. And so we stretch those, that increases the force in the muscle. And we're doing that without using ATP, right? It's just being stretched. And then we do the concentric contraction. And initially in that first bit of the concentric piece, we're going to reclaim that elastic energy. Okay. And that's why stretch shortening cycles are so beneficial, in that as long as we do our concentric component immediately after the eccentric component, so before the cross bridge can release, we reclaim a portion of that energy because it's just a stretched elastic band. So that's what's happening. Does that help?
Yeah, that makes more sense.
Yeah, so just understanding that direction of joint motion and muscle creating the torque are two separate things.
Okay, but like one side's doing one thing and then another side's doing that, like contradicting that motion, right? Depends on the motion.
It depends what you need in order to do the activity. If you need your quads, for example, in that sitting one, as you sit down, if you sit down slowly, you have to have your quad, even though your knee is flexing, because it's flexing as you sit down, right? It's going from a straight knee to a bent knee. So you are absolutely flexing your knee as you sit down. But as you sit down, especially if you're doing it slowly and controlled, it's your quads that have to be on to control that motion down. And so the quads are the muscle, your knee extensors are the muscle that have to be on, and your knee is flexing. That's what the question wants you to tell it, that you are flexing your knee and that you are using your quads or knee extensors to do it. And then the next step, which this question doesn't ask you, but we do get to it, is, well, if the quads are on which means the quads are the agonist muscle. The muscle that has to be on is the agonist muscle. And we are flexing our knee. So if the extensors are on and we're flexing our knee, then we have an agonist muscle that is contracting eccentrically. Okay.
Okay.
And does that work?
Yes, yes, much better. Thank you.
Okay. Any other questions on that question?
I had one is more so on the practical approach of the stretch shortening cycle.
Sure.
Yeah. So another example I was thinking about would a pitcher throwing a baseball be an example of
Yeah.
Yeah. Okay. Okay.
Yeah, because if they don't hold back here and just hold, they go back and then they throw. And if they do it right, they should get some stretch shortening out of it. It's plyometrics. I mean, plyometrics is stretch shortening cycles. Okay. Anybody else on that? If not, Aaliyah?
Hi, Dr. Moore. Just a quick question. Would you mind explaining the difference between the parallel elastic component and the series elastic component, please?
Absolutely. So muscles have, they have all sorts of proteins in their, sorry, in their makeup, right? Not just actin and myosin, but all the portions that, let's just find, you have your various sarcolemmas and all the things that go around the outside and come out to the tendons, that even if you don't have a cross bridge formed, there's no cross bridge formed. If you pull that muscle, eventually it's going to get longer and it's going to act like a big elastic band. And the that's the main thing. You have this, all of the portions that make up the pieces that are intact, all one piece from tendon to tendon, will get stretched as that muscle gets longer, and they will act like an elastic band. And you do not need to have any cross bridges formed. And when we do the force length curve, you know, the passive component of the force length curve is created by those parallel elastic components. Yeah, and so they're going to get long. The other thing about those passive elastic components, you stretch out a muscle, you don't have your muscle on, you have the muscle relaxed when you're doing it, but you just lengthen the muscle, right? You pull till you feel it in a muscle because you've lengthened the muscle. And that's what stretching is, you know, I stretch out. I don't have my flexors on, but you can feel it in there because I'm pulling them back, right? And there's a lot of muscles there to stretch if you do that. So again, these aren't on, they're just being stretched. And because they're not on, the cross bridges aren't formed. So I'm just pulling all the other elastic things that are in parallel to the cross bridges. That's why it's called parallel. Parallel and passive end up being the same because they are structures that create an elastic force without going through the cross bridge. On the other hand, if I have a cross bridge that's formed and I pull the muscle, such as when I have an eccentric contraction and I pull, I am actually going to stretch structures which are in line with the cross bridge. So I have a cross bridge that's formed and I stretch it out, and anything in there, the cross bridge itself, for example, will get stretched, and it'll also act like an elastic band. But it's a temporary elastic band, because as soon as that cross bridge releases, it'll swing back into place. It'll literally be like letting go of an elastic band. Okay, those are called in series because they're in line. In series is another, it's actually comes from electricity, series and parallel. Series just means it's in line with the structure. So it's a series elastic components are components that are in line with the cross bridge and only get stretched if the cross bridge is formed. That help? Okay. Any other quick questions? I do have to go soon.
It's not really a question, but I'm not sure if you seen, but the slides for lecture 13 aren't up on eClass.
I've already, they'll be up today.
Okay, thanks.
Yeah. Anything else? Okay. In that case, we